My name is Nicholas. I'm finishing my second year at UC Davis, and I'm talking about measure homology, specifically how it relates to a classification problem of what's being called wild algebraic topology. For any topological space, I can take the topology and generate a Borel sigma algebra. And from there, I can define a sign measure, which is like a measure, except I'm allowed to take on negative values, although I'm not allowed to take on both positive and negative infinity. For any measurable or continuous function, I can define a push forward. And if I take this function to be continuous, if I have a sign measure that is finite, meaning it does not take on positive nor negative infinity, and it's compactly determined, for us, we can think compactly supported, then the push forward will have the same properties. It will be finite and compactly determined as well. I can endow the space of singular n simplices with the compact open topology. From there, I could define sign measures, and I'll define just ones that are compactly determined and of finite total variation. The space of these measures defined on singular n simplices will be called measure n chains. And this is a real vector space. An example is a Dirac measure, which will take in a set, and if the indicated singular simplex is in the set, it will return a value 1, and if it's not, it will return the value 0. In the Euclidean sense, there is an inclusion map of the faces of a standard n simplex. And I can take these maps, which I know are continuous, and extend them of maps between the spaces of singular n simplices and n-1 simplices. And this operator will take in a simplex and map it to another simplex representing the face. This allows me to define a boundary operator on my measure chains, and the definition is very similar to the boundary operator of singular homology. The homology theory that's associated to this chain complex is called the measure homology, and it was first seen in Thurston's work to show of a rigidity theorem. So it's also called the Milnor-Thurston homology theory. Regardless, it satisfies the initial axiom, although it does not satisfy all the axioms for arbitrary topological spaces. So the Ellenberg-Stenrod axioms are satisfied when my space is a CW complex, and this gives me an isomorphism between singular homology with real coefficients and my measure homology. Furthermore, that isomorphism is shown through this very fundamental map, which will take a class that is represented with a singular simplex to the Dirac measure that's supported on that singular simplex. It was later shown that it's actually isometrically isomorphic with respect to the appropriate norm, and that's the norm that you generally would put on a homology class to generate a simplicial volume idea. What I was interested with Professor Jha is an interpretation for the zeroth homology group. So for singular homology, the zeroth homology represents how many path components there are. So here's an example where this also holds at the bottom, although we'll see that that interpretation fails. If you have these constraints, if you know your space is compact and countable and metrizable, you can show, for example, a convergent sequence space that the measures that you can define on it, the zero measure chains is isomorphic to the space of absolutely summable sequences. For spaces that are not CW complexes, you do not satisfy the axiom of a disjoint union factoring as a direct sum of the spaces, although you do get an inclusion of the chain spaces themselves. This is all stemming from this result where the Warsaw Circle homology was calculated, and it was shown that the the zeroth homology has an uncountable dimension. So this is very similar to the space before, as in there's one path connected component, although they're definitely different enough to produce a different result for this measure homology. So the work I'd like to continue to do is to detect what is this zeroth homology, measure homology trying to detect, and I believe it's something to do with the type of local connectivity that exists. Thanks.